In this video, we're just going to continue with some more ICE tables, just different things to keep your eyes open for and to practice the concept of setting up an ICE table, because again, this is key to your success on the AP test. There's always one for response that it's all about equilibrium. Like, I guarantee you will do an ICE table somewhere on the AP test, probably multiple ICE tables. So we've got this equation. We are forming gaseous hydrogen fluoride from hydrogen and fluorine gases. We have an equilibrium constant of 1.15 times 10 to the second. So that's like K. So we can make a note. K equals, there's our constant, at a particular temperature. In this experiment, 3 moles of each component are added to a 1.5 liter flask. Fun. Calculate the equilibrium concentrations of all species. All right, let's do our ICE table. So we'll rewrite the equation. H2 plus F2 forming 2 hydrogen fluorides. We're going to ICE. Okay, so now here's one thing you have to be careful of. When you plug numbers into an ICE table, you have 2 options. One is pressure, which would be common for something like this, where our components are gases. The other option is concentration. If it's a solution, you might see molarity, or in this case, we need to plug it in as moles of gas per liter of volume. So I need to take that 3 moles of each component and divide by the 1.5 liter flask. So when I put this in the ICE table, we're going to start them off as 2 moles per liter. Everybody's 2 moles per liter. And even this guy, initially he's 2 moles per liter. Okay, cool. So we don't have any zeros. We're going to have to calculate Q. We'll compare Q and K to figure out the direction of our shift. But keep your eyes open for that. A lot of times, by accident, people will just plug in like 3. And then they'll be like, oh, darn, it was 3 moles in a 1.5 liter flask. Yeah, your only options are concentration or pressure. So here we do have to plug it in as moles per liter. Notice too that this is not the ratio from the balanced equation. This is what we've initially been given. And I'm going to guess that it's probably not at equilibrium. At equilibrium, we're going to change by this ratio in the balanced equation. We're going to change at a 1-to-1 ratio of reactants and a 1-to-2 ratio between reactants and products. Let's calculate Q and see what direction this thing's going to shift, huh? Okay, so Q looks just like K, but we use initial data. So we're going to have products. 2 moles per liter of HF squared, check the ratio from the balanced equation, all over 2 moles per liter of hydrogen to the first, and 2 moles per liter, and this is the fluorine. And that's to the first. Ow. Well, that's easy. 2 squared over 2 times 2 is 1. Duh. Q equals what? Do I have to show work for Q? Yeah, you do. I know it's really easy. So, I mean, you got to show that you knew how to switch this thing. Like, do I shift it forward, reverse? How do you know? By comparing Q and K. How did you know what Q was? I plugged the initial data into that equilibrium expression. So even though you got something that's really easy like this, you could have done it in your head. Yes, I need to show work. And then I'm going to compare Q to K. Q is way smaller. And so again, these are a comparison of products over reactants. Q is way too small. So in order to increase Q up until the point where we equal K, we need to shift this thing forward. We need more products. Shift forward. Excellent. So we know we're shifting forward by comparing Q and K. However, we don't know by how much. We weren't given any equilibrium conditions. That's all right. We'll plug this in as x, right? We can do this. So we know we're shifting forward. The reactants are going to go down by x. Whoopsie, minus x. Hello. Now here's another thing that you have to be careful of. These guys are going to change by the ratio in the balanced equation. So we're going to form products. We're going to form 2x on the product side. Everybody changes by the ratio in the balanced equation. By the 1 to 1 to 2 ratio. It's probably one of the most common things that people will miss on an equilibrium problem. And then they'll just slap themselves in the face because they're like, oh my gosh, I knew that I needed to change it by that ratio. And they just accidentally forget. Oh yeah, that's 2x. We know we're shifting forward, so the products will increase, the reactants will decrease. But remember to change by the ratio in the balanced equation. So at equilibrium, this will be 2 minus x, 2 minus x, and 2 plus 2x. So we'll set this up, we'll solve for x. We know k. K was 1.15 times 10 to the second. Let's say 115. Products, 2 plus 2x. And we still need to square that. Here's another common mistake. When I set up the equilibrium expression, it's almost like I'm using that ratio twice. I have to add 2x, plus I still need to square it when I set up my equilibrium expression. On the bottom then, we're going to have 2 minus x to the first and 2 minus x to the first. Which actually we could probably simplify this, huh? Could we just take the square root of both sides right away? Is that okay? Can I just go like this and like that? Because you see how like really on the bottom it's like 2 minus x times 2 minus x. So let's take the square root of both. And let's say this is about 10.7 equals 2 plus 2x over 2 minus x. Alright, so again, a little algebra, a little blast from your past. We'll cross multiply and say 21.4 minus 10.7x equals 2 plus 2x. And then let's combine like terms and all this fun stuff. I'll subtract the 2. Let's call this 19.4 equals. And then we'll add the 10.7 and say 12.7x. X then equals 1.53. Fabulous. I can plug this back into my ice table and away we go. The more ice tables you solve, there are some common mistakes, like forgetting the 2x or forgetting to square it again in your equilibrium expression. But after a while, you kind of know what to look for, and these things really are near fun. Like I would almost call this fun. All right, so we're going to plug in x, and then we're done. Okay, so my 2 reactants will be the same at equilibrium. Hydrogen and fluorine will be the same. They will be 2 minus x, which would give me about 0.47 moles per liter. And then my product, my hydrogen fluoride, is 2 plus 2x. Whoa, that's a funky looking F. Hydrogen fluoride, 2 plus 2 times x, 5.06 moles per liter. There she is. Not bad, right? I like this example. It's a good example of just little twists and things to keep your eyes open for that now you will never get wrong.